Welcome back. So today we'll start a new topic on electricity. Um, in chapter 18, so that's the start of this main topic. It will probably cover a couple of chapters here in the textbook, but in today's lecture, we'll just talk about some of the topics here to start with. So we'll talk about electric charges, insulators, and conductor. What's the difference between the two? And then we'll talk about the interaction between charges, which is governed by Coulomb's law. So let's jump in right now. So we probably have heard electricity when we are little. Actually, we are using electricity every day. So and then you can also experience electricities from some of the like the playground. If you watch kids slide down from the slide, sometimes you see their hair stick up because there's electricity generate as they slide down between their body and the slide. Okay, so that's called static electricity. And then in the winter, which is the season right now, a lot of times if you touch the doorknob, which is metal, and you didn't realize you actually already have static electricity generate your body, and then once you touch it, you feel that the electric shock. That's because there's charges on your body. Okay. And you probably have heard it was the Benjamin Franklin first demonstrate that lightning was actually related to electricity. This is a very dangerous thing to do, so you guys probably don't want to do that. It's already proven. All right. So something else you can do for fun about static electricity is you can actually, if you have a rod of rubber, if you rub it against wolf or fur here, then you can actually be able to pick up small particles as like pieces of papers, small pieces of papers. So before you are doing that, it does not have charge on it, so you couldn't do that. But after you rub it against the fur here, then you can pick it up. Okay. So fundamentally, it's because there's charge on the rod. So similarly, you can do some demos if you are teaching some science class to kids. So because there's charges around, so for charges, if you have same charges, positive in here, negative and negative, they will actually repel each other. Okay. And then if you have positive and positive, then they are the same because they are like charges, they will repel each other. If you have opposite charges, positive and negative, they actually will attract each other. Okay. You might be wondering how it was this assigned which ones are positive, which ones are negative, but the sign of charges was originally just given. Okay, so as just this is a convention. If you were to discover charges, say a few hundred years ago, then you can actually call them opposite in the opposite way. Okay, all right. So fundamentally, because materials are made of atoms, and in the atoms, there's protons, neutrons in the nucleus, and then there's electrons that's orbiting around the nucleus. Electrons are so-called negatively charged. So depending on what kind of the material you have, that means different atoms have different tendency of um, losing the electrons or keeping them. So if you have one material rub against another one, okay. So for example, um, rabbit fur, they have tendency of actually losing electrons. So the negative electrons are taken away, so they are positive charge after you rub against other materials. Okay, so this is a list or table of materials with their relative charging with rubbing against each other one. Okay, so rubber will have tendency of getting negative charges. So if you have a rubber against a rabbit fur, then rabbit fur will be positively charged. Rubber will be negatively charged. Okay, all right. So by charging either if you are rubbing two materials against each other, you are not actually creating new charges, okay, because it's just one of them loses electrons to the other. So overall, you still have the same number of electrons and protons, okay. So it's the objects are initially neutral, electrical neutral, but you are not actually creating more electrons or protons in that sense. So the process, if you consider the two objects together, is still a really charge conservation. Okay, so you're not creating new charges. So we can take a look on the mechanisms behind if you have a charged particle around small pieces of, say, papers. So fundamentally, if you have a rod charged, in this case with positive charges, when you approach the rod to a small pieces of material, so they are made of molecules or atoms inside of them. Now, positive charge will attract negative charges. So if you have molecules, they are probably polarized, or you can actually make them polarized because of the charges that you have here nearby. So then the molecules will be polarized. So one side of it will be more negative, and then the other side will be more positive. So then there will be net attract force between the two because the negative charge is closer to the rod here. Okay, and then you'll see how that in just a few minutes when we talk about electrostatic interaction, the forces between charges. Okay, they are inversely proportional to charge to separation. So negative charge closer to the positive charge, those should be more attractive than this guy to this. Okay, to the positive charge on this side. All right. So charge is actually quantized. Okay, so that means it actually if you have a certain amount of charge, so they are coming as increment of a certain number. Okay, so it's a very small number, but it's not like continuous charge increasing in that sense. Okay, so it's coming in multiples of electron charge. Okay, so that's the minimum amount of charge you can have. So E is equal to 1.6 times 10 to the minus 19 coulombs, okay, for the unit. So charge in coulombs, that's its SI units. Electrons have minus of 1.6, 0 times 10 to the negative 19 C. Protons, on the other hand, have 1.60 positive 1.60 times 10 to the negative 19 C of charge. Okay, so if you have 1 coulomb of charge from the electrons, which means negative in that sense, then there's about 6.25 times 10 to the 18 electrons. Okay, so this is a constant number you can use. Even if it's not given to you. So electron charge for electron or proton is 1.6 times 10 to the 19. Keep in mind, for electrons it's negative, for proton is positive. And also, these are some also constant numbers you can use. Mass of an electron is a constant number, 9.11 times 10 to the negative 31 kilograms. Mass of a proton is 1.673 times 10 to the minus 27 kilogram. And mass of neutron is 1.675 times 10 to the minus 27 kilogram. Okay, so those are all constant numbers. So those four constant numbers, okay, that you can use directly, even though if they are not given. Now, you probably don't have to memorize them. I will give you those numbers in the formula sheet with the problem or in the test, but it might be a good idea if you are taking an MCAT test later on. So they might or might not be given, okay, to you. All right, so let's take a look on the example here. It says a system of 1525 particles, each of which is either an electron or a proton. Okay, so these particles are either electrons or protons, has a net charge of minus 5.456 times 10 to the minus 19, 17 coulombs. How many electrons are in the system? And what's the mass of the system? Okay, so you can see this total charge is negative, so you will have more electrons than protons because electrons are negative 1.6, 10 to the minus 19. Protons are positive at 1.6 times 10 to the negative 19. Okay. All right. we are looking for how many electrons. So we are given two numbers here, total number of particles and total charge. And we know each of their charges, right? So we can set up two equations, then we can solve for the two unknowns of protons and electrons there. Okay, so let's take a look here. I'm going to just write out um, the known numbers we have. So in total, equals to 1525, and then the total charge. Okay, so C total, let me call it C total. Okay, is minus 5.456 10 to the negative 17. Okay, so these are the ones given. And then some constant numbers. Okay, so we are having electrons and protons here. So for the charge of a proton or electron, we'll just say E. Just keep in mind for electrons it's negative. Okay, so this is 1.6 10 to the negative 19 coulombs. And we also need masses for the proton and mass for the electron in the second part. Okay, so these are for electrons, it's 9.11 10 to the negative 31 kilogram. For protons, it's 1.673 times 10 to the minus 27 kilograms. Okay. All right. So let's call number of electrons as capital N sub E, and then number of protons as capital N sub P. So the total of these two add up is 1525. Okay, so 1525. And then for the charges, for electrons, so M number of electrons times minus of E, okay, because electrons are negative charge, and then plus protons times positive E, that is negative 5.456 into the minus 17 coulombs, okay. And then here, this is a constant number, so we can actually divide both sides of the equation of the second equation by E. Okay, so let's do that. So if we do this divided by E, this divided by E. So that means the E and the E, the E and the E will cancel. Okay, so they will both cancel. And E is just use the number 1.6 times 10 to the negative 19 coulombs. Okay, so E is equal to that. So on the right hand side here, if you do that divided by that, okay, that actually gives you negative 341. Okay, so then now we have this equation as the first equation. And this second equation, we can rewrite it. Okay, so we can tie these things a little bit up. So we can do a minus sign here. You can say minus of NE plus MP is actually equal to minus of 341. So this is my equation 2. So I got equation 1, I got equation 2 here. And then I can solve for either of those, okay? Two equations with two unknowns. We are looking for number of electrons in part A, so we can probably do that. We can do, typically you can say MP, it will be equal to 1525 minus this NE, right? And then, so you do MP, right? One unknown in terms of the other unknown, and then do substitution to the second equation. So this MP will be replaced by that, right? Okay, then you can afterward, this equation will just have NE as the unknown there. You can solve for NE there, okay? I have another way of doing this. So because I have these two equations, I can do equation 1 minus equation 2, which means I'll do the right-hand side of equation 1 minus the left-hand side equation 1 minus the left-hand side of equation 2. That should be equal to right-hand side equation 1 minus right-hand side equation 2. Okay, so if I do this minus that, you can see MP and MP will cancel. Okay, but NE minus of NE, that will give me 2 times of NE. So I will have 2 times of NE equals to this guy minus this, right? So this guy minus of that, that means you add them up. So that will give you 1525 actually plus 341. Okay. So then divide both sides by 2 here and there. It will give you the number of NE. Okay. So that will tell you your NE is equal to 933. Okay, for your part A. And so we will be done with part A there. And in part B, we are looking for the total mass. Okay, so total mass, that means the mass of electron. Okay, so that many of electrons times that, and then plus we'll need to figure out now this time MP. Okay, so MP, you can use that. So you can actually figure that out in pi as well. So MP then is equal to 1525 minus this 933. Okay, or you can do equation 1 plus equation 2 that will get rid of NE, and then you have 2 of MP, and then this guy plus that guy. Okay, so you also tell you the number of MP, the protons, will be 592. Okay, so if you get this one greater than this one, then something must be wrong, because you should have more negative charges, which means more electrons than proton. Okay. All right. So we have also have that number of protons. Then we can calculate the total number of the mass. So mass total then should be equal to MP times MP plus NE times ME. Okay. So 592 times 1.673 10 to the minus 27 kg plus 933 times 9.11 times 10 to the minus 31 kg. Okay, that will give us 9.91 times 10 to the negative 25 kilogram. Okay, as the total mass of the system. Okay. Again, it's a small number because masses for electrons and protons are really small. Okay. All right. So let's go back to the slide. All right. So moving on to the next section, we will take a look at the difference between conductor and insulators. Okay. So definition for the two is if you have materials that can actually conduct electricity, then they are called conductors. If not, they are actually called insulators. Okay, so simply like that. But the difference between the two is for conductors, they can conduct electricity because they have electrons. They are free to move about inside the materials, which those electrons are called conduction electrons. Now, most metals, they are conductors. They have free electrons that can move around. Okay. For insulators, they do not have those electrons that can move from atom to atom. Okay. So for insulators, all the electrons are bounded closely to the nucleus, so they are not able to move around. So then they are insulators. Okay. All right. You can charge materials by, again, in section 1, we talk about you can rub two materials against each other. So then the material has higher tendency of losing electrons, will lose electrons, and then the other one will gain electrons. So you make two conduct. Okay. You can also, or you can make, or you actually made the two materials having charge. Okay. You can also give charge to a material by um, contact. If you have a charged material that in contact with an uncharged particle. Okay, so then the charge will distribute partially to the uncharged particle. So in this case, let's say if you have a device like this, which this two piece can actually move, um, yeah, flexible to move. So when you have this guy approaching this one, so this is made of metals, they're conductors. So then you have positive or negative electrons that will be close to this end, closer to the charge, positive charge right here. The other end then will be positive charge. So then the two pieces metal will be actually repelling each other, so they make an angle. Um, Now you can have this guy touching this metal on the top here, so positive and negative they will cancel out. Um, then leaving just the positive here, and then after that you can remove this guy. Okay, so then this whole thing will be positive charge. Okay, so this is a another way of to charge a material. Um, you can also do charge by induction, which means you have two pieces of conductors, and then you have a charged material moving close by. So then one side or the object closer to this charge rod will now be negative charge, and then this side will be positive charge because electrons can be freely can move freely around. So then electrons will go this way, leaving that side um, positive charge. After that, you can separate these two. Okay, so because this side is now then will be more negative charge, this guy will be positive charge. And then you can remove this. So then both of these two balls, metal balls will be charged. Okay. The same mechanism here for if you just have one single piece of the metal here, you can have it actually in contact with the ground. So then so this is what you do first. First, do not ground it, but approach a positive charge rod close to the metal. So then one side of metal will be negative charge, the other side will be positive charge. Now connect to the ground. So then the positive charge will be repelled away, further away into the ground. And then after that, you can cut this grounding wire. So then the whole thing will be negatively charged. Okay. Now you can remove this rod. So then this guy will be negatively charged. All right. We'll move on to the next section on the interaction between charges. So this is governed by Coulomb's law. So that gives you how to calculate this law, tells you how to calculate the force between 2 point charges. Okay, so if you have two charges nearby each other by a separation of r, so then the force between the two will be equal to a constant number k, called Coulomb's constant, times the charges of the two, the absolute values of the two. So you can have a positive and negative, or both negative or both positive. Okay, and then divide by the separation between the two charges and score it. Okay, so this is force. It's called Coulomb's force or electrostatic force. Um, the SI unit is newtons. So that gives you the magnitude of the force between the two charges. Okay. Coulomb's constant is 8.99 times 10 to the 9th newtons times meter square over Coulomb square. Or you can simply just use 9 in this case. That would be fine because 8.99 is almost 9, about 1,000th of a difference. So it wouldn't be a big factor when you are calculating the numbers for the force. Okay. So this gives you the magnitude of force. We know force is actually a vector, so it should have a direction. Okay, so the direction on the force. So if the two charges are like charges, they will repel each other. So then that means that the force on the two charges will be pointing away from each other. If they are opposite charges, then they will be attractive to each other. Okay, so in that sense, so for positive, the force will be repel each other. So both charges will experience force, electrostatic force, and then opposite charge they will repel. They will be going towards each other. Okay, and it's a convention. Typically, if you have repels force, we say the force is positive, and then if you have attractive force, we will say that's negative. Okay, all right. So you can see Coulomb's force or electrostatic force is in many ways very similar to gravitational forces of two masses. So if you remember, gravitational force is a constant number also times the two masses and divide by separation squared. Okay, so in large distances, the um, between two massive objects, actually, the gravitational force governs there, okay, rules there. Now, in smaller distance, in electrons and protons, then it's more likely electrostatic force is the main force, okay. So let's take a look on atom inside atom. So for like hydrogen atoms, so the distance from the proton to the electron is 5.29 times 10 to the minus 11. And we can take a look at the gravitational force between this electron and proton. Use the gravitational law here. So gravitational constant times the two masses divided by the distance. That will give you 3.63 times 10 to the minus 47 newtons. But the electrostatic force between the two here, you can use Coulomb's law, the constant, Coulomb's constant times the two charges divided by the separation square. That gives you 8.22 times 10 to the minus 8. Okay, so this guy is much bigger than that guy, although they are both small, but this one is bigger than that one for about 39 orders of magnitude. Okay, so much bigger. All right, let's take a look on a quick example here. It says um, two charges, 13.1 microcoulomb and 26.1 microcoulomb. The magnitude of force between these two is 1.77. So what's the separation of the two? Okay. So this one it's about the electrostatic charge. So then it's Coulomb's law. We can write it out. The force between the two charges are given and the charges are given. So then from the Coulomb's law, F equal to K Q1 Q2 over R square. So it's like absolute values of the two, but they are both positives. So then they are you don't necessarily have to do the absolute sign. Okay. Change camera over there. All right. So you are given the force, you are given these two, this is a constant, right? So you can solve for that guy. So basically we are solving for that. Okay. So then from here we can see if you multiply both sides by R square, right? And multiply by R square here and there, and then divide both sides by F. Okay. So the R square cancel, the FF cancel. So then you will get R is going to be, so R square on the left hand side and then all this on the right hand side. So R square equals to K. We'll just use Q1, Q2 because they are both positive, okay? Divided by F, okay? So then to find R, we'll square root both sides, okay? And square root. So R equals to square root of K, the constant number 8.99 times 10 to the 9th newtons meter square over Coulomb square, and then times Q1. They are given in the problem. So we can take those numbers, 13.1 micro, that means 10 to the minus 6, and then times the other one, 26.1, 10 to the minus 6 Coulomb as well, and divide by the force given 1.77 newtons. Okay, so you can check at the units to make sure the as dimensionally consistent. C square cancels C here and there, newtons cancels newtons there, and then square root will give you meters, right? So that's R, so that's consistent. So R then will be given after you punching all the numbers in your calculator correctly. It will tell you that the two charges are separated by 1.32 meters. Okay, so again, applying Coulomb's law, F equal to K Q1, Q2 absolute values over R2 square, and then just rearrange to find R here. All right. Now going back to the slide. Um, okay, switching back camera. All right. Okay, second problem here, or second example here. So this one, again, it says 2-point charges. The first one with a charge of, again, positive, but then the second one is negative. So positive 3.13, again, microcoulombs, 10 to the -6, and then the other one minus 4.47 microcoulombs, separated by 25.5 centimeter, okay? So you probably realize that you have to change the centimeter to meters because this one is not in the SI unit. It says find the magnitude of electrostatic force experienced by the positive charge. Okay, so magnitude. Then we'll apply Coulomb's law again. Okay. So here again, we are using the Coulomb's law F equal to K. For the magnitude is this equation again over R squared. So plug in numbers. Okay, so let's say this is part A, 8.99 times 10 to the 9th. Okay, so it's 9, it's like 9 times 10 to the 9th. Okay, so it's probably a little, you guys can memorize this constant. And then absolute value in this time is 3.13 positive, 10 to the -6 coulombs, and then times negative 4.47 times 10 to the -6 coulombs. So that absolute value will turn the negative sign to positive. And then over 25.5 centimeter. So that becomes that. Okay. So then punching everything into a calculator correctly, this gives you 1.93 newtons. All right. So that's the magnitude. In B, it's asking is the magnitude of the force experienced by the negative charge greater, less, or the same as the positive. Okay. So for Coulomb's law, it's the interaction, the force between the two charges. So then if one charge experience that much of force, then the other one should be also experience that much of the force. So it's kind of action and reaction force from Newton's third law. So this guy then should be the same. Okay, so the same, we'll say that kind of action and reaction pair forces. Okay, all right. So let's go back to the slide. If you have multiple point charges, okay, then to find the force on a particular one, you'll then just find the force from the second one to that one, and then the third one to that guy, and then the fourth one to that, okay? And then you'll add those three forces up on that guy. But remember, force is a vector, or forces are vectors. So when you add them up, you need to add them in the format of the vector addition. Okay. So again, you can use component method we learned in physics 1, or you can do a triangle method if we're just adding two vectors up. Okay. So F vector with the arrow on top, F1 is equal to this guy. Those three add up. Okay. Graphically, you can do that. Just draw. This is the head to tail method. Okay. Graphically. All right. We'll take a look at one example here. So it says three charges in this at the corners of this equilateral triangle as shown here. So it's asking you to rank they are equal charge amount, so they are both equal to Q. One is positive, two is negative, but three is actually positive again. Okay, so and it's asking you to rank the three charges in order of increase in magnitude of electric force they experience, indicate ties where appropriate, and then given directional angles and net charge of the net force by charge 1, by charge 2, and by charge 3. Okay. So we'll take a look on this guy here. So let's see. Um, so there are three charges, multiple charges, right? So then um, let's take a look at one at a time. So here, so between one and two, they are opposite charges. So then it will be the charges will be or the force between the two will be attractive. So you should have a force from here and then so let's say from here. And it's going to point towards that guy there. Draw an arrow here and then an arrow there. Okay. Not the prettiest one, but that's okay. And then there'll be a force from here and then pointing in that way, repulsive. Okay. And that goes like that and that. Okay. Oops. All right. See if I can erase it. Maybe let's just start from the beginning. So this first force there, and then there's this force there. Okay. Forces, the magnitude F should be just the K constant, right? Times Q. Q1, it will be Q, and then Q2 will be negative Q, but if we take absolute value, so then that gives you Q score, right? And then divided by A, the separation, A is the side of that. So A, let's say A is the side of the equilateral triangle, okay? So these two should be having the same magnitude or the same length because K constant and Q's are the same. A is the same for equilateral, okay? So then these two add up. Graphically, you can say, so put this guy here. Let me see if I can change the color. So if I put this guy here, move this guy parallelly over, right? So it's pointing in that direction. So then the total force will be in this direction, okay? And this will be a flat one because this guy is a 60-degree angle. This guy is also a 60-degree. So 60-degree here, 60-degree here, and this is a straight line, right? So straight line there. So then this guy should be 60 as well. Okay, so this angle should be 60 as well. And this one is equal to this. So then that gives you this as an equilateral triangle as well. So this will be flat. Okay. So that means this total force on charge one will be then again equal to this guy. Okay. Now let's take a look on this one here. Force by one on two will be that in that direction. A bit wiggling, but should be the same length as this that guy. And on these two again, they are opposite charges, so this guy should be going in this direction as well. Okay, maybe not terribly too much in that case. Okay, and then the total force on this one will be. So we can draw this one, move this guy parallelly over here. So it's going to be something like there, tail and head and tail method. Okay, so this will be the total force. Okay, so this is that those two are the same, and then this one is that. So they look like this one is bigger than this. Okay, so we can see force on two so far is bigger than force on one. So this is a FR1. Let's call it FR1 for the total. Okay, and then this is F of two for the total. And then we can analyze for the force on the third one. So again, attract force, change it to original color there, about that length there. And then here should be repulsive. So it's going in this direction there. Okay. And for the total force on this guy, we'll move this one parallel over here, and then we'll have a head to tail method again here. So total force should be pointing from the tail of the first one to the head of the second vector. Okay. So here again, 60° there. You have another 60° here. And actually, let's see. This one's 60. This is a straight line. Okay. And then we move this guy parallel over here. So this guy is 60. Okay. And then these two are the same lengths. So then this will be again an equilateral triangle. So this will be 60. Okay. So this angle then will be another 60. Okay. So this guy will be minus 60 for the angle. Okay. And then this guy for the angle is 0°. Okay. The angle here, so these two are the same. And then this is 60. So this is 60. Okay. So that means this guy will be, these two angles are the same angles. So then they are 30° apiece. Okay. But this total angle is 60. So then this guy is also 60. Okay. Or actually 30, because this is 30, this guy is 30. Okay. So this angle for F2, it goes from here to this horizontal line there. So it's 120 because this one is 60, 120 plus that 30 over there, so it's 150. Okay, so 150 degrees of angle there. All right, so I think we have all the information. F1 and F3 should have the same length. Okay, so for A, it's not pretty here, but F1 in the order of increasing. Okay, so F1 equals to F3. And less than F2, because F2 is the biggest one. Okay. And then for the angles, this is A, or this is for the F1. Okay, so this is B, angle for B. This guy's B, RB. For C, for 2, this is for C. Okay, there. And then this is angle for D, RD. All right. Okay. So it's basically kind of on this one, we are not given any charges, but we can just look at their magnitudes relatively. So F1 equal to F3 less than F2. And then for the angles, 0° for B for F1, 150° for F2, and then minus 60 for C because it's actually below the horizontal. So we say it's negative. Okay. All right. So So, um, so for Coulomb's law, it applies to point charges. But if we have a spherical charge distribution, then it can also apply to those spherical distribution as well. Okay, so then the distance you are measuring should be from center of sphere to another center of sphere. Okay, in that case, just to put that out, and then later on we'll talk about more about like charge distributions that gives you what forces how you calculate on different, not a lot in this class, but there's probably a little bit on that too. Okay, all right, so quickly review what we learned today. So we talk about charges. There's positive charges and negative charges, and they are quantized in the increment of one electronic charge or a charge of proton E, 1.6 times 10 to the negative 19 coulombs. Electrons has negative of that, protons has positive of that. And then we look at insulators and conductors. What's the difference between them? So conductors have conduction electrons, insulators they do not. Okay, and we look at the Coulomb's law, which gives us the way to calculate the forces between two charges, or multiple point charges. Okay, so F equal to K Q1, Q2 absolute values over R square. Okay? And then that K is a constant number about 9 times 10 to the ninth in that magnitude. Okay, we'll stop here for today, and then I'll see you guys next time.